Hello viewers, I discuss today few important MCQ type of questions which are very much useful in various exams like MC entrance or NET, whatever may be. It's very helpful. Let's watch this type of questions. I discuss today the part of abstract algebra in group theory, especially elementary group theory. First question is, if G be a finite group and order of G is 6, then and H is a subgroup of G, then what will be the possible order of H? We have to discuss it. And it is clear the order of G is 6 given, and H is a subgroup of G, then possible order of H. Now here we consider the Lagrange's theorems. That order of H must be divisor of order of G. Then we factorize these 6. What will be the factors of 6? If we consider 1, and we can say that's 1 that also divides 6, 2 divides 6, 3 divides 6, it's the notation, 4 doesn't divide, and 6 also divides 6. So here we are choosing these options 1, 4. This 4 doesn't divide 6, so this option is incorrect, wrong. Next, 1 divides 6, 2 divides 6, 3 divides 6, 6 divides 6. So this option is correct. 2, 4. 4 is not possible and none. So only correct option is second. Now we are going to the next step. Next questions. What are the generators of Z4? But if we study the concept of a Z4 idea, that's a modulo, that's a mod Z concept, and it is clear that it is integer concept. Z is nothing but the integer. It's a notation in set theory, Z4. So integer modulo 4. How to construct this? And if we consider this cyclic group, because we are taking this integer shape of format like this Z shape, that's form the element of nothing but this, consider this element 0, 1, 2 and 3. But what are the generators actually? That's a cyclic formations we find, and this is the generators. And if we are considering this operation system of 1 and 3, certainly it will be, if we add it in terms, we are finding this 0. That's the modulo 4, that means 0. So it will be the identity element. And if we consider 2, 3, that's 5. That's 5 means 1 mod 4. 1 mod 4 is not the generator. So only generator is identity element is 0. And this concept 1, 2, which is also not possible. So only option is 1 and 3. This is our option. And now we are going to the next questions. If G be a cyclic group of order 21 and H is a subgroup of G, this is given, and order of H is also given 7, then we have to find the nature of the subgroup, and it is cyclic or non-cyclic or any other simple group or none of these, whatever may be the options. So it is clear order of H is 7 and order of G is 21. So we have to consider a theorem. A subgroup of a cyclic group is cyclic. How to prove this is a subgroup? This is a given, and by Lagrange's theorem, it is subgroup, it's clear, and order of G is 7 and order of H is 21. So here 7 must divide 21. So order of H must divide order of G. So it's clear, and it's a subgroup, and G is cyclic and H is a subgroup of G. It's also given, and by Lagrange's theorem we can prove order of H is there. So order of a cyclic subgroup must be cyclic. It is the property. And elementary theorem. And we are now going to the next questions. If G be an abelian group of finite order, then every element of G have its own inverse, every element of G having its own inverse, and in inverse in this group, that's an inverse doesn't exist, and none of these options are given. So if we consider like this group, if A B belongs to G be a group, and if this inverse exists, like A inverse and B inverse is there, and every element is own inverse, that means if A is equal to A inverse and B is equal to B inverse, we considering this property like this, AB whole inverse, that means AB is equal to AB inverse, and this property is AB inverse is equal to B inverse A inverse. This is a property of group. AB inverse whole inverse equals to B inverse A inverse, and B inverse is we can find it, B inverse is equal to B and A inverse equals to A. So B inverse is B, A inverse is A. So AB is equal to BA. If we are taking this concept, A is equal to A inverse, B equals to B, or B inverse equals to B, or B equals to B inverse, whatever may be it is, we can write in this manner. Then AB is equal to AB inverse, and AB inverse is by the property of AB inverse by group property, B inverse A inverse, and B inverse equals to B and A inverse equals to A. So AB equals to BA. This is a formation of abelian. So we can see this result, and option 1 is correct, that every element of G have its own inverse, and G is a finite abelian group of finite order, then every element of G have its own inverse. This is correct. And in this way we discuss few questions which are very much useful. In later sections I will discuss many questions in my next video. Keep watching. If you like this video, like it, share it, and subscribe the channel. Thank you.